This presentation treats about an experimental project conducted on an all-precast pre-stressed concrete bridge beam reinforced with bonded fiber reinforced polymer. This project was realized thanks to a cooperation between CEREMA, IFSTAR and ASFA, and the experimentation took place in Autun laboratory, which is a part of CEREMA. So first of all, I present the context of this experimental project, then I'll talk about the real old viaduct from which a beam was recovered, and I present actually this beam, the program tests, the huge instrumentation which has been provided on the beam, and second I'll describe the tests and their results which led to some conclusions and perspectives. So a large amount of precast pre-stressed concrete bridge beam viaducts, so from now I'll talk about PPCBB viaduct, were built in France before 70s. They were quite easy to build, but the fact is that they were designed as fully pre-stressed and made from compressed and perfectly waterproof concrete. However, many problems of corrosion appeared on pre-stressed cable of many viaducts, and this corrosion led to certain vulnerability of those structures. And the problem is that it's quite difficult for supervisors to evaluate the residual stress in pre-stressed cables and then to evaluate the level of vulnerability and to manage with these problems. It turns out that in many cases, after only a few decades, it was necessary to repair some of those viaducts. And this reparation can be carried out by using traditional methods like the addition of pre-stressing tendons or passive steels, but the reparation could also be carried out by using composite materials, which are more and more used in civil engineering. Indeed, FERRIER can easily repair, strengthen and adapt structures to changing requirements, and they can prolong the useful life of the structures. However, although a great deal of progress has been made in these fields, questions are still raised concerning the efficiency of using bonded composite materials to reinforce pre-stressed concrete structures, which are in a critical state, and especially when bonded over existing cracks in the structures. So after this short introduction, I'm going now to focus on our tested beam from a real old viaduct. So this viaduct was built between 1952 and 1954 over River Doubs in Clerval City using PPCBBs. And the viaduct suffered from waterproofing and concrete injection defects, which led obviously to a huge corrosion on pre-stressed cables and finally to the demolition of the viaduct in 2002. And during its demolition, a beam was recovered in prevision of an experimental testing on a real structure. So the beam is 30 meters long and 1.3 meters in height. It's made up with 21 pre-stressed cables. And the beam had 2 stress bend cracks at the beginning with a maximum opening of 0.2 millimeters. And so these cracks are located in section S2 and S4. So the objectives of the test program are on one hand to help contractors managing PPCBB viaduct risks by improving surveillance, auscultation and evaluation methods, and on the other hand to get a better knowledge of how bonded FERRIERs work on pre-stressed structures. And we wanted especially to know how would work FERRIER when bonded on existing cracks. So first of all, preparatory investigations of the beam were necessary, like listing the beam's initial visible defects, characterizing the concrete, or determining the real position of the cables. And the residual stress was also in pre-stressed cables was also a fundamental element and was evaluated thanks to a crossbar. So concerning the strengthening work, So purulent carbon fiber plates were bonded on the underside of the hill to strengthen the beam. So those plates were applied in 2 stages. A first stage of 2 packets of 3 plates were fixed to the side of the hill, and a second stage with 2 other packets of 3 plates in the central part of the hill. And a load was applied between these two stages of reinforcement, as explained a bit later. The carbon fiber plates were carried out by FERRIER company. Their dimensions were 50 by 1.4 square millimeters, and they are maximum 24 meters long. So the beam was then tested thanks to a 3-point Lloyd bending test. The beam was actually tested in 3 steps. So a first test, which was a cracking test before any strengthening, up to 240 kilonewton. It was in order to monitor the evolution or apparition of cracks. A second test, which was also a cracking test after the first reinforcement stage, up to 300 kilonewton. So after this second stage, the 2 packets of 3 plates were cut in section S2. And after that, the second stage of reinforcement was applied, and a final bending test up to the rupture of the specimen was carried on. So now, in order to monitor the beam as complete as possible, 187 measuring points were recorded. So there was on one side the traditional instrumentation with temperature sensors, bending measurements in kilometers, strain gauges on concrete with 5 seconds. So strain gauges on concrete and strain gauges on carbon plates. For the strain gauges on carbon plates, there were 2 instrumented sections, and for each section, several gauges were bounded between carbon plates and under and below the last carbon plate. And on the other side, there were non-traditional instrumentations. There was an instrumentation by fiber optic sensors with 2 optic fiber embedded in concrete in the upper face of the beam, and optic fibers also between the carbon plates and below the last carbon plate. There was also an instrumentation by acoustic methods. The first acoustic method is local acoustic emission investigations. It consists in detecting acoustic waves induced by a sudden release of energy, as the one caused by crack initiation or crack growth. And the second acoustic method is the global acoustic monitoring with wireless sensors installed along the beam. They can detect and record acoustic waves due to wire breaks. And finally, curvature measurement. So a very huge and redundant instrumentation. So after setting up all those instrumentation, bending tests have been carried out. So during the first cracking test, before any strengthening, crack in section S4 open, and section S4 lost its monolithism at 160 kilonewton, and several cracks also appeared next to the loading axis. During the second cracking test, after the first reinforcement stage, the bending of the beam was quite similar to the bending of the unstrengthened beam, and Navier diagrams were also quite similar. And the final bending has taken place in several steps. So first step, where shearing of the side bonded composite plates occurred, so from the first stage of reinforcement, at a load of 640 kilonewton, 14 kilonewton. and with a bending of 20 centimeters. There was a flaking of the concrete and of the concrete surrounding the pre-stressed cables between section S2 and S4. So you can see it here. And after that first step, the effort mobilized for the load continued to decline. Then a second step with an extended delamination, another shearing of the bonding composite plates, this time in the center of the hill, occurred, with another flaking of the concrete surrounding pre-stressed cables. And this second step occurred for a load of 588 kilonewton with a bending of 26 centimeters. And finally, the definitive break of the beam occurred in section S2 for a maximum bending around 40 centimeters. So during the third and final step, we observed a behavior modification of the beam around 450 kilonewton. This behavior modification was monitored by inclinometers and bending measurements and by strain gauges on concrete, which recorded a modification of the curvature of the section and a modification of the neutral axis. This behavior modification was also monitored by gauges on pre-stressed cables, which detected a rupture of several wires within the same pre-stressed cables, and by acoustic monitoring. We observed that the first rupture of a wire occurred at a load of 400 kilonewton, and that the first rupture of several wires within the same cable occurred at a load of 450 kilonewton. So we registered a behavior modification at around 450 kilonewton and a rupture at 610 kilonewton, but we had a higher prediction with our model, and we obtained an estimated ultimate load of 747 kilonewton without considering safety factors, and 674 kilonewton considering safety factors. So this demonstrates the difficulty of correctly evaluating the structural security of PPCBB of a viaduct. What's more, the estimated ultimate load of the beam without any strengthening is around 520 kilonewton, which is not far from the first behavior modification. So it's very important because it indicates that carbon plates can bring some security as soon as the behavior modification is monitored on a viaduct. And we can see that the security margin between the behavior modification and the ultimate load is increased with a safety factor of 1.5 without FRP and 1.36 with FRP. Note that the difference between our calculation and the experimentation can be attributed to corrosion of pre-stressed cables. So we really need to make a full autopsy of the specimen to understand what happened. So concerning the effect of carbon plates, we observed the positive local effects of the plate in preventing cracks from opening. You can see here under the hill the diminution of the crack opening. And what's more, we observed an improvement of the distribution of the fissuration cracks thanks to the carbon plates. Yes. So finally, in conclusion, this test on real PPCBB showed the difficulty of correctly evaluating the structural security of a PPCBB viaduct, which has been seriously damaged by the corrosion of the pre-stressed cables. We've also checked on this test that all our monitoring instruments are complementary and cross-check one another. They all indicated the changes in performances of the different sections of the beam. And finally, we observed that bonded FRP help controlling crack width and distribution cracks. So this test will lead to recommendations concerning an instrumentation which could be implemented on damaged PPCBV viaducts to ensure better monitoring. And a full autopsy of pressed cables will be realized in order to help readjusting predictive models. Just to finish, shear test was recently led on half of the beam after the flexion test. So it was made last June. We observed a rupture of the specimen for a load of about 200 tons with fracture inclined according to concrete strut. Contrary to what was expected for this kind of test, we observed a ductile failure. And I won't say any more because the analysis is underway. Thank you for your attention.